After 30 shining years of super roadway service, we are searching for ways to dig out of the crumbled concrete. President Eisenhower envisioned conduits of commercial and personal travel in 1956, when he signed the first of many road bills. Today, only 57% of our paved jungle is rated good. 43% is disintegrating before our eyes. Historically, much of the research and attention has been focused toward our primary highways, while our secondary and county roads slowly deteriorated. Now, the attention is directed at improving these local roadways. Patching potholes and reconstructing torn roads is further complicated by gaining financing. Over 2,700,000 miles of our roads are under the jurisdiction of city, township, or county agencies. This constitutes 70% of our total highway mileage. Approximately 92% of the roads in the state of Kansas are maintained by city and county agencies. Most depressing is the fact that 75% of these roads do not qualify for federal aid. This is true for most Midwestern states. Local officials are left to search for innovative and cost-effective methods to simply maintain the existing road system. With our search for alternative methods, more attention is now focused on the use of fly ash to help upgrade our road system. Produced during the combustion of coal, fly ash is the fourth most plentiful resource in the United States and is available in locations where aggregate is in short supply. Fly ash produced during the combustion of subbituminous coals obtained from Wyoming and other western states produces an ash having self-cementing properties. Designated as Class C fly ash, the ash has properties similar to Portland cement. Upon exposure to water, a hydration reaction occurs, forming cementitious compounds. The Class C fly ashes do not require the addition of activators such as lime or Portland cement, as is required for Class F ashes produced during the combustion of bituminous coals. 6 coal-fired electric generating facilities, having a total annual production of approximately 575,000 tons of Class C fly ash, are located within a 90-mile radius of the Kansas City metropolitan area. Due to the large quantity of high-quality ash available and aggressive promotion by the utilities and their brokers, a large amount of ash has been used for stabilization purposes throughout the eastern and central portions of the state. The Jeffrey, Iatan, and Lacine generating facilities are the primary sources of ash utilized for stabilization purposes throughout the area. These units have a combined annual production of approximately 450,000 tons, constituting almost 80% of ash production in eastern Kansas. The recycling application has grown from experience developed from use of the ash as a stabilizing agent for soils. Ash stabilization can be categorized into 3 general areas: drying the soils to facilitate compaction, treatment of soils to reduce shrink-swell potential, stabilization to improve subgrade support capacity or shear strength. The recycling process consists of pulverizing the entire pavement section to the surface of the subgrade and adding a self-cementing fly ash that, following recompaction, would stabilize the mixture. The unstabilized mixture would consist of aggregate, crushed limestone or gravel, asphaltic-bound particles, and fines consisting of aggregate and subgrade soils. Compaction of the pulverized section would produce a soil aggregate section. Typically, the amount of soil and fines present would result in the aggregate being suspended in a matrix of fines with very little intergranular contact or interlocking between the coarse aggregate. The shear strength of the fines is generally relatively low compared to a graded aggregate base and would therefore severely reduce the stability of the compacted mixture. Also, shear strength of the fines would be further reduced upon saturation, decreasing the durability of the compacted mixture. The addition of self-cementing fly ash is intended to stabilize the fines present in the compacted mixture. This stabilization would increase the shear strength and durability of the compacted material. The primary objectives of the demonstration project were to demonstrate the feasibility of recycling existing pavements by stabilizing with self-cementing fly ash, to formulate an acceptable range of structural coefficients for design of pavements using the recycled materials, to evaluate the range of fly ash contents required to stabilize a variety of recycled materials, to evaluate whether adding commercial retarders can enhance stabilization, to develop mix design and construction procedures and specifications, to monitor environmental aspects. Demonstration sites were selected in Kansas City, Wichita, and Topeka, Kansas. All three represent major fly ash market areas and are conveniently located within reasonable distances from major generating facilities. All three sites were existing roads slated for reconstruction. Construction costs were borne by the participating city or county government, with funds provided by the research program for laboratory and field testing. Two separate Class C fly ash sources were utilized for the study. Fly ash was obtained from Kansas City Power and Light's Lacine Station and from Kansas Power and Light's Jeffrey Energy Center. Both generating facilities burn coal from sources in the Powder River Basin of Wyoming. The demonstrations began with a series of test borings at each site. The borings were used to classify the existing pavement and subgrade conditions. Samples were also obtained for laboratory study. The stabilization process begins by pulverizing the existing pavement. Depth of pulverization must be carefully controlled to minimize incorporation of subgrade soils into the recycled section. After pulverization, the material is lightly compacted and shaped to allow uniform distribution of fly ash. The fly ash was transported to the sites in pneumatic tankers and discharged in windrows on the center line of the road. After the ash has been dumped on the roadway, the windrow of ash is bladed uniformly across the roadway to achieve lateral distribution. The fly ash particles are spheres much like marbles, which gives it the appearance of muddy water as it gently flows in front of the blade. Winds of 15 to 20 miles per hour cannot blow the ash off course once it has been dumped from the truck. Once the fly ash has been distributed, mixing with the pulverized material began. Water required to achieve the optimum moisture content was introduced directly into the mixing drum. Control of moisture is very critical for the recycling process, as the moisture content must be maintained within a fairly narrow range to attain maximum potential strength. Because Class C fly ash begins reacting as soon as it comes in contact with water, compaction of the recycled section must be completed as rapidly as possible. Initial compaction was achieved with a vibratory pad foot roller operating directly behind the recycler. Several passes were required to achieve compaction. After initial compaction, the roadway was shaped to final grade and the surface was rolled with a smooth wheel or rubber-tired roller. Periodic wetting of the surface is required for continued hydration of the ash. The recycled section is intended to function as a base course section, providing the primary structural element of the pavement. Application of a wearing surface is required, as the recycled section does not have adequate abrasion resistance. The future for fly ash is a promising one. Since the completion of recent fly ash projects, other successful projects have been completed in a 7-state area in the Midwest. Long-term monitoring of the demonstration project will provide a basis for more rational design and implementation of the process on future projects.